Hello, I'm Han-Sung Kim, and I'm working at National Radiation Emergency Medical Center, which is a part of Korea Institute of Radiological and Medical Sciences, KIRAMS. And the title for today is Recent Studies on Computational and Physical Human Phantoms at KIRAMS. Before we go on to the main presentation, I'm going to briefly introduce KIRAMS. So one of the role of our institution is to conduct research on radiation protection and dosimetry. And we also do dose reconstruction for accident situation using computational and physical human phantoms. Today, I would like to introduce two different research topics conducted at KIRAMS using human phantoms. One is related to physical phantoms, and the other one is related to computational phantoms. So first topic is to construct physical phantoms, which is a physical version of adult mesh type reference computational phantoms. And the second topic is to estimate the dose using computational phantoms and Monte Carlo simulation. So the first topic is development of physical phantoms. For physical human phantoms, there are many applications, such as radiodiagnosis, radiotherapy, radiation protection, and medical imaging. And one of the main advantages of physical phantoms compared to Monte Carlo technique is that exact source term or irradiation geometry is not required. So this is especially useful when a radiological incident is occurred and lack of radiation source information. So it looks good. However, for dosimetric purpose, there are very few commercially available existing physical phantoms, such as CIRS atom phantoms and Alderson radiation therapy phantoms, which is called rando phantoms in the past. So although some quantities can be measured using these phantoms, the thing is that they do not represent reference person. So they are not reference phantoms, which means we cannot estimate those quantities defined for reference person in radiation protection field. Recently, IRPA publication 145 has been published, and this publication describes mesh type phantoms designated as reference phantoms. And many improvements have been made, and the phantom is provided in mesh format, which can be used as a design of 3D object printing. So this is one of many advantages. For 3D printing, there has been exponential growth in popularity in 3D printing technique due to its revolutionary capabilities. Despite these opportunities, conducting methods and appropriate materials for dosimetric phantom are not well studied before. So, in the objective of this study is to establish a novel method to construct physical phantoms using 3D printing technology. Also, using this method to develop a physical counterparts of adult mesh type reference computational phantoms for physical measurement. So in this presentation, I'm going to briefly explain the method, and for more detailed information, we are planning to write and submit a scientific paper. So for 3D printing technology, component materials and the manufacturing method are really closely related. And for dosimetric phantom, practically 3 tissue equivalent materials were used for soft tissue, lung, and bone respectively. So we also adopted these 3 materials to compose our phantoms, and we combined 3D printing technology and casting method to develop the physical phantoms. So for soft tissue and lungs, 3D printing was used. But for bones, casting method is used, and the 3D printing output was used as mold material. For component materials, our aim was to find or develop appropriate tissue equivalent materials to meet two criteria. One is physical densities, and second is effective atomic number. So in order to meet this criteria, mixing impurities with high atomic numbers were avoided. And the result is shown in this table. For physical density, the results were more or less identical, and effective atomic number were also very close to the goal, considering that it's very hard to control each elemental composition. Here is outline. So left blue box describes software element and right box describes hardware element. So original STL data is a kind of design extracted from MRCPs was used as design, and segmentation was conducted, and then sliced, and dosimeter holes were designed in grid pattern. Then the slices were 3D printed, and the bone material was poured into cavity of 3D printed output. And dosimeter holes in grid patterns were made, and holders were printed so that the dosimeters can be inserted in order to measure observed dose to tissue or organs. So here are some photos of manufacturing process for your information. So this is 3D printer, and this is output of 3D printer, and we use this output as mold for bones, and this is dosimeter holders, and we printed slice number at the final stage. This figure shows the developed physical phantoms in the present study. So the left one is female phantom, and the right one is male phantom. The phantom includes also arms and legs, and the phantoms can stand upright, as you can see. So also figures on right are the example of the slices. So we can distinguish the tissue or organs due to circuit screen with color. So here is the characteristics of the developed physical phantoms. So we newly developed the phantom using hybrid manufacturing methods, which is 3D printing and casting. And also the phantoms correspond to the MRCP's geometry. So thanks to the MRCPs, also the physical phantom includes mostly all tissue or organs for dosimetric measurement. And it is sliced at intervals of 2.5 centimeter in axial direction, and 38 slices for male and 35 slices for female, with assembled arms and legs, and dosimeter holes in grid patterns. This is one of application we recently conducted. So the phantoms were utilized in intercomparison experiment for retrospective dosimetry. We assumed an industrial radiography incident, and the dosimetry quantities can be measured physically. As I mentioned, the second topic is related to computational phantoms. We made a massive pre-calculated database for industrial radiography incidents. So I will explain briefly this topic. Industrial radiography is a method to inspect materials for hidden flaws by using short wavelength electromagnetic radiation, such as high-energy photons. This is one of the most high-risk radiation practices due to the frequent use of very high activity For example, 50 curies radiation sources near workers. So it's really dangerous. We need to estimate the dose for this kind of incident. Before I mention the objective of the present study, I would like to point out that mesh-type phantoms are deformable. So these are MRCPs in different postures provided by Hanyang University. So standing postures, walking, bending, kneeling, and squatting. So we can represent the similar posture to real workers. Here is the objective of the present study. So in this study, we selected representative exposure scenarios with consideration of industrial radiography incidents in the past. And based on these scenarios, a pre-calculated comprehensive database of those coefficients was constructed using Monte Carlo simulation and adult male version of MRCP in different postures. With this method, there is no need for time-consuming procedure when we estimate the dose, and moreover, the method can provide the doses in terms of different postures with the help of mesh-based human phantoms. We chose 4 representative exposure scenarios for industrial radiography incidents with comprehensive consideration of various materials. So first scenario 1 is when radiation workers handle the source with their hands. So scenario 2, when workers step on the source. And number 3, when workers work nearby the source. And scenario number 4, the worker works nearby the source. This is similar to scenario 3, but scenario 4 is for field work. To construct a database for each scenario, appropriate source location were selected and those coefficients of appropriate dosimetric quantities were calculated. And the database provides the dose coefficient for discrete points, so interpolation process is required. And the unit is like this. And we chose iridium 192 and cobalt 60 as radionuclide, which are frequently used in industrial radiography. And Jant4 Monte Carlo toolkit was used. This is example of exposure scenario number 3, and the source points are 10 centimeter equidistant points from the surface up to 100 centimeters in 4 directions. So this is the part of the result of scenario 3. So in addition to the result shown here, we have established a massive pre-calculated database by Monte Carlo simulation. So the database is like a lookup table. So for the results, generally, the male-only effective doses of cobalt 60 are approximately 2 or 3 times higher than those from iridium 192. And the male-only effective dose is higher when a source is located in front than when it is located in the rear, due to the location of the major organs, including colon and stomach, is in the front of the body. This is concluding remarks. So in these present studies, we developed the physical counterparts of MRCPs for physical measurement using newly developed manufacturing method using the 3D printing technology. And one of the main advantages of these phantoms is that the phantoms faithfully follows MRCP's geometry. Also, there has been progress in the method of manufacturing, and further studies will focus on comprehensive validation of the developed physical phantoms with MRCPs using Monte Carlo simulation and measurement. And for the second topic, we made a huge database. So we believe that our database, pre-calculated database, can provide a convenient option to estimate those for industrial radiography incidents without highly trained professions, without time-consuming procedures. Thank you for your attention.